To introduce today's speaker, Professor Eli Yablonovitch. It's a very long CV here. I was just told to keep it short. There's a whole list of awards and fellowships I won't even go into. I encourage you to read the bio on the website, and it's really a great honor and pleasure to listen to the talk today. I was fascinated by the abstract to learn about the fluid photons. So please, Professor Yablonovitch.
Okay, great. It's great to be at HKUST again, and I will cover something that I covered a few years ago here at HKUST, and it has to do with the new discoveries in photovoltaics. And photovoltaics is how we convert light. So light is our most prevalent resource, especially if you go out on a sunny day. There's an amazing amount of energy surrounding you. And so I'll kind of explain the new discoveries that enabled the efficiencies to go to records now, but also you're going to see that there is a problem. And a subject like this you cannot discuss purely as a scientific subject. You also have to look at the social context, especially here in China, what's going on. And I'll get into that. You'll see why this is not normal science, because I have to actually say a few words about what the industry is doing in China. And what I'll get to is a new opportunity, a new science to make a new type of heat engine where light is used as the working fluid. And so heat engines, we were just discussing at lunch. We have the steam engine. Is it 200 years old already? I think it's more than 200 years old. And their steam was the working fluid. And we'll see more recently electrons were the working fluid in thermoelectrics. And now we're going to have light. And this is a rather new opportunity. So let's go on. First of all, to remind you all that solar panels are a big industry in China, at least $20 billion a year. And you'll see in a minute that there's actually quite a bit of regret in China that they over-invested in the solar panel industry. So you'll see what happened there. That's also quite fascinating. Now, scientifically, though, something very important happened about 5 years ago. And that was that the records, which had been unchanged for a very long period, like 2 decades, the record was unchanged. And then in a very short time, it jumped from about 25% to close to 29%. Now, to give an idea, this is very similar to records in athletics. So the Olympics are coming up, and there's we will see if we watch it on television that when you break a record, you break it by 1/10 of a second. And maybe even less than 1/10 of a second. It's the same in solar cells. We break the records by 1/10 of 1% in terms of efficiency. But here the record jumped by 4% all at once. This is not due to some marginal improvements, but it's due to some new scientific insight, which I'll share with you. And this record efficiency is coming completely from voltage. Current is not doing anything. The voltage suddenly jumped by 1/10 of a volt. And that is now creating new opportunities for us, because now we are getting very close to the theoretical limits. So what happened is we were stuck at 25%. Now we're jumping toward the theoretical limit, which is 33.5%. And there is some new physics in this region. Once you get close to 29%, there's actually some new physics, and I'll show the new physics on this slide. That if you open a textbook on solar cells, they'll say, well, the light comes in and gets absorbed, and you create an electron hole pair, and then you collect the electron hole pair, and that's how a solar cell works. And that is the outdated idea. And the new idea since 5 years ago is rather different. And it says, yes, the photons come in, they get absorbed, you produce an electron hole, but they don't necessarily get collected. What if they recombine to produce another photon? You give a photon back. So then that photon bounces around, gets reabsorbed, re-emitted, and reflected and reabsorbed and re-emitted, and finally, eventually, maybe collecting an electron and a hole, but of equal importance, sometimes just leaving the solar cell. Seemingly very wasteful that you would emit light, but we made the remarkable discovery that if you allow the solar cell to emit light, you will suddenly you get much greater efficiency. Now, the second picture has inside the film, inside the photovoltaic film, you could have 40 or 50 suns of intensity, even though there's only one sun of sunlight coming in. And so this is very surprising. It says for it to work correctly, you have to build up a big photon gas inside. And this, by the way, you will not see in any textbooks yet, but it undoubtedly will get there. But it's clearly the way to go in terms of getting good performance. Now, where did this come from? Well, actually, Shockley had some idea of this. And he said, look, aim for the highest external luminescence efficiency. So when your solar cell is working very, very well at the open circuit point, for every photon of sunlight coming in, there will be one photon in the ideal world. It would give back a photon of luminescent, just wavelength shifted, but basically one photon in and one photon out. That's perfection, and you achieve then the ideal. And if you fail to get one out for every one in, you will pay a price. And the price is this thermodynamic formula, which has the luminescence efficiency in it. And it says you ideally at open circuit, you should be giving every photon back. And if you fail, you will not get as high a voltage. So I have here explicitly, this is a minus sign. You're losing voltage. So this led to the world record, and I'm gonna show you the films in just a minute. But this is now the world record. By the way, in this field, you don't report your own world records. You have to send it to a government lab, and this was sent to the national lab in the United States that does the checking. So what was learned by this is that if you have a good solar cell, let's say 25% efficient, please stop worrying about the electrons and holes. So all of the modeling in all the textbooks that it's all about the electrons and holes, that only applies for very bad solar cells. For good solar cells, it's all about managing the light and being successful at re-emitting the light. And so this led to a slogan, and it is my favorite slogan. It is a good solar cell has to be a good LED, and a great solar cell has to be a great LED. And it's very counterintuitive because it says that to work well, it has to actually give back some of the photons. And this is, people are very greedy. They say, why should I give anything back? But that actually results in the highest performance. And this was sort of explained in this paper from 2012, that this is the case. Now, the consequence of this is that a whole nother series of records have been broken. You could make a dual junction cell. I won't dwell on this. I do have the cells with me. So one of the great things about this field, I can actually carry them into a talk. And so these are the actual solar cells that do this. These are the films. And they have this property. If you make, what I have here is just gallium arsenide. If you add the indium gallium phosphide, you can actually increase the efficiency. So that one is now 31.5% efficient, also a world record. Okay, and then there's yet a further world record. This is a very noteworthy one, using the same principle of great solar cell has to be great LED. This was done at the National Renewable Energy Lab in the United States. And it was not single junction, not dual junction. It was quadruple junction. Obviously they got a higher performance. This is actually the world champion photovoltaic cell, 38.8% efficient. A very bright young guy by the name of Miles Steiner did this. And I said, congratulations, Miles. I met him at the conference. Congratulations. He said, oh, this is nothing. 38.8, I can get to 40. Okay, and so this is actually the world champion cell, which they published in January of this year. And it gives you an idea of what can be done. So this concept owns the single junction, dual junction, and quadruple junction record. You say, why didn't they do the triple? There just wasn't any point. They just went ahead and did the quadruple. And why didn't this happen before? Because this field is an old field. It goes back to the even before the early 50s. And I asked myself the same question. I think the barrier was psychological. And maybe I had fewer psychological barriers, but I also had barriers. I asked the student, please, no one has ever figured out the theoretical efficiency of gallium arsenide. It's, many years ago we figured out the theoretical efficiency of silicon, but why don't you do gallium arsenide? No one's done it. And so he goes and does it, and he comes out with fantastic numbers. And I say to him, well, that's great. We'll probably never achieve those kind of numbers. And it ended up back in a drawer. Okay? But it was all there. But it's just that until you start seeing this tremendous performance coming out, it's a little hard to have the conviction of the theory. That's sometimes a little difficult. And it's all about getting this external luminescence. Now, one of these other psychological barriers, they say, oh, gallium arsenide. Well, who's interested in gallium arsenide? It's so expensive. If you're making cells for space use, sure, you would use gallium arsenide. No one cares what it costs, but people say it's expensive, but actually it's not true. It has not been true for many years, and that is that there's a way to peel these cells from a substrate and reuse the substrate. So this would be the substrate. You reuse it, and you peel. And I'll give you an idea how this works. This is, by the way, an industrial process. There's a company in Santa Clara that does this and sells it commercially. Unfortunately, I no longer own any shares in that company because we had to sell it to an eccentric Chinese billionaire, Li Hejun. But I'll tell you how the technology works. They prepare hundreds of these wafers, and the trick is there's a great selectivity with acids. There's great selectivity. Some things are soluble, some not. It turns out aluminum arsenide, it's a perfect lattice match to gallium arsenide, but it chemically is very different. It gets attacked by acid, and gallium arsenide does not. So they take a cassette with hundreds of these wafers. They put them into acid. Go away, long coffee break, a couple hours, come back, and it looks like nothing happened. But they take a vacuum chuck, and they go, and they just pop off, and you get exactly this film, and the substrate is ready for reuse. And this has become, this was developed gradually over a period of time. It was speeded up. This was in the mid-90s. They were doing 2-inch diameter. Now we do 6-inch, and this is more or less what I've got here. It's this flexible thing. Now, this much I covered a few years ago when I came to HKUST. I should mention about the company. It is presently owned by a Chinese company, Energy, and but they're in production. It is a commercial scale process, and leads to very high efficiency. This was happier times when my co-founder and I, Harry Atwater, and myself, we were at a board meeting, but we were forced, due to the economic situation, we were forced to sell it to this young, very wealthy gentleman from Beijing. And this gives you an idea what some of the market is unmanned aerial vehicles, the curvature, the fact that these things curve and bend, you can put them on wings and so forth. So this is all good. Now, so that is the scientific part, which I can summarize, is if you want a successful solar cell, make sure it's an LED. Make sure it's the world's best LED. Okay. Now, but it's part of a big industry, the solar economy. What's really happening in the solar economy is we have one little factory in Santa Clara, California. It doesn't have that much capacity. Today, to have a serious factory, you need 1 gigawatt a year of capacity. China has many of these factories, but is not happy about it. And I'll mention, first of all, what is the technology? It is not gallium arsenide, it is crystalline silicon. And the efficiency is not that great. It's maybe 15 to 23%. but it has 90% market share in the industry. But here's the real problem, is that China overbuilt too many factories. This happened about 5 years ago. And the worldwide production capacity, China alone has about 60 gigawatts of the worldwide production capacity. And adding the rest of the world in, you get maybe 70 gigawatts a year of capacity. And the problem is that there's only, even today with very low prices, only 50 gigawatts a year of demand. So you have an oversupply situation. And when there's an oversupply, there's a price war. And then the price settles down at such a level that nobody is making money. And all of these Chinese factories are losing money. And so they're stuck. And you could ask how this happened. And there's been some speculation how it happened. And by the way, I've spoken to many of the students here, and they're all aware of the situation. All the students I spoke with, this should not be news. Is this news to anybody here? Raise your hand if this is news. Nobody wants to admit that they haven't heard this. Okay, so how this happened is that, as you know, like in every country, the government tries to create jobs. And in China, many provinces said, we are going to be the world capital of solar panel manufacturing. And they built factories. And then the central government said, oh my God, we have way too many factories. And they gave out an edict, unless your factory is 1 gigawatt a year, which is world scale, you're too small to compete, we'll have to ask you to close your factory. That meant every province very rapidly increased the size of their factory to go to 1 gigawatt a year of capacity. And very quickly we end up with a situation. There was overcapacity by a factor 2, and the price war, nobody can make money at this price. So this is very bad. However, the field as a whole is very interesting. This is something should not be part of a science lecture, should be part of a business school lecture. And in business school, there's something called the learning curve. And when I entered this field, which was a long time ago, 1980, the price of the solar panels, you can see this is $30 a watt. And that was, let's see, I think that was in current dollars, a very high price. And everyone was convinced that we would always have a high price. But one of the things they teach in business school is something called the learning curve. And what the learning curve says, as you produce more, you get smarter and smarter about it, and the price comes down. And business school professors have studied this, and they've noticed that many things are similar. If you increase the integrated total historical production by 2 times, you get smarter by 21.5%. So the price drops by 21.5% with every time you double the cumulative production of the entire world. And people laughed at this. I remember, I didn't take it seriously. My boss, though, kept trying to convince everyone. I was at the Exxon research lab. This was the lab of the company that's called ESSO here in Asia. And they, at that time, were very committed to solar cells, but they kind of lost interest. But what happened, sure enough, they were right. Not the company, but my boss was right, and the price kept dropping and dropping over a period of time. And this line is this learning curve, 21.5% for every factor 2 in production. And you can see roughly the year that production was achieved, and you see a few bumps along the way. So let me explain the bumps, because the bumps are also very interesting. The bumps the price went up instead of going down, and this was around 2006 because there was a silicon shortage. Why was there a silicon shortage? Is because the Green Party in Germany demanded subsidies, and suddenly there was a great demand in Germany. They didn't care what price it would be at, and so they were ready to pay any price to get solar panels, and sure enough, the price went up. This was a very good time to start a company. And however, then things got bad. There was a silicon shortage, but then the shortage ended, and you ended up with overcapacity because too many factories were built in China. And now we are below the learning curve, and that's why nobody's making money. We're down here in the 50 cents. So roughly speaking, this is very interesting for those of us in science. We should learn about some other fields. The price actually dropped by 100 times over a 35-year period. And the drop was not because some business school professor said it would drop. Drop occurred because there were discrete technological improvements that made it happen. And you could point to that, well, they did this better and that better. And so the price went down. But you have these swings. Sometimes it overshoots and sometimes it undershoots. It's very interesting. You can actually go to the web. You can look up the spot price. So the spot price is now only 53 cents a peak watt, which is a price at which everybody loses money. Unfortunately, they can cover their variable costs, but they cannot cover their fixed costs. But in a sense, it's a great historical contribution in that there are now 227 gigawatts of panels installed. So this is really a huge amount, and starting to dwarf, starting to become comparable to nuclear power. It's a large amount. Now, so I want to pause here because we get a little bit away from. Does anyone have any questions about the non-scientific aspects here? Yeah, go ahead. No, I think there's some learning going on, and we will jump from here, which is the last time we were where we should be, and the projection is that we'll come back to equilibrium around here. So maybe the price won't drop very much, but the demand will catch up and the price will stabilize. Right now, it's not a healthy situation, but there is great hope in the industry that this crisis will end, but nobody knows when. So we will get back to the learning curve, but we will get back at a lower price. So something will have been learned during that time. Okay, now let me mention one more thing about this field. Germany is a leader because of subsidies. Germany is a leader in installing solar panels. And in fact, Germany has installed so many solar panels that at some times of the year, half of the electricity of Germany is coming from solar panels. And you can see that I've chosen a specific day, May 26th, 2012, which happens to be a Saturday. And why a Saturday is because there is less demand, so solar can be a bigger portion of the total supply. So on weekends, the industry shuts down. Offices are closed. Okay, now the other thing that's interesting is why did I choose a day in May and not a day in June? Well, June is more sunny, but the solar panel is a type of heat engine that's actually more efficient in cooler weather. So it's actually, you get more power in May than you do in June. So you see here a remarkable thing. Half the electricity was coming from solar. Now the other half of the electricity was coming from things you could not turn off easily, like nuclear. And even coal plants, they don't like to cycle that well. And so this is sort of like the maximum they think they can do. They have not done any better in the past 4 years. Let me show you geometrically what the problem is. If you look at all of this solar power and make a triangle like this, say, wow, that's great. Half the power, but only at noon and only on a Saturday. And now in the morning, you get nothing, and in the evening, you get nothing. So it's a triangle. And then look at the 24-hour period. I'm sitting on the 24-hour period, and it's a much bigger area. And so I have that entire area, which is non-solar. So what it tells you that even, and if you do the ratio of areas of triangles to rectangles, even on the best day of the year, only 20% of the electricity was coming from solar on the best day of the year. It's in May. What about November? November, almost nothing is coming from solar. So if you average over the year, Germany receives only 7% of its electricity from solar after spending 100 billion euros. So this is a lot of money, actually. Okay? And Germany, wherever you take the railway in Germany, you look out the window, every farm has solar panels because of the subsidies. They have installed 40 gigawatts. So it's a lot for one country. But here's the problem. They have an oversupply. They're actually paying the neighboring countries to take the electricity at peak times. And then you say, well, but China has a different kind of oversupply in manufacturing plants. So we say, well, what if all the factories in China just continue to produce panels for the next 30 years? That means every country will be oversupplied, just like Germany is today. And after 30 years, all these Chinese factories can build 2 terawatts, and then the whole world will be oversupplied, and there's no justification for the next 30 years to build another factory. There's no justification for any research. It's a very sad situation because there are so many factories. Some of them are idle. They will eventually be turned on. And to justify R&D, to justify new production capacity, I claim that new and different application markets are needed and that the solar panels are not that good a match to the electric utility. And that you saw 7% penetration only with the electric utility. There's a lot of other kinds of energy. It's kind of pathetic. So to make a further impact, maybe we'll get to 10% impact on the electric utilities, but it doesn't look that great to me. So some of the things that are being investigated are using the electricity to make fuels. And this is very simple. You take the best solar cell, like these very good solar cells, and you use the electricity to electrolyze water. You have hydrogen. And there are actually lots of applications for hydrogen. And so that would actually be a pretty good market, a huge market, bigger than what we have now. But there are other things that you can do that really have nothing to do with solar. So I'd like to mention a few of these other things that are enabled by the new science. So because we now have extremely efficient photovoltaic cells, we can do things that we couldn't really think of previously. And I'll give you one example. I think I discussed this previously on a visit to Hong Kong UST, but mostly something new having to do with using the photovoltaic films as refrigerators, and heat engines. Very amazing stuff. Since we're, for the very first time, making really efficient photovoltaic cells, we're getting closer to the theoretical limits. And I've already argued that the LED is the inverse of the solar cell. So we are, for the first time, making very good LEDs. Some new ideas become very timely. One of them is thermal photovoltaics. And I'll mention what it is that if you have something very, very hot, you have a Planck distribution. And in the Planck distribution, you have a tail of big photons. And these big photons can be used in a photovoltaic cell to make electricity. So forget the sun, you convert heat to electricity. Now, this is an idea that's been around since 1960. And 20 years ago, they already made a car that uses this, but the efficiency is not very high. It's only 20% efficient. So why is it so inefficient is we have so many photons that are just too small to be useful in a photovoltaic cell. You have all these small photons. And we have to do something with that. And the smart thing to do is to send these photons back to the heat source. Let's say that's the heat source. They get rethermalized, they emit the Planck distribution again. You strip out the 10% of the high energy photons and you send them back. So you simply need to have a selective and efficient way of sending the unused photons back. And you get this kind of for free. Now I should mention, people have spent the last 50 years doing this the wrong way, making, for example, at MIT, I don't want to criticize MIT, I have some friends there, but they were trying to make some spectrally selective filter on the heated surface, and it is just not durable at these temperatures. So the easier thing by far is to notice that in semiconductors, you have a step function in absorption. So if you absorb, then you can use the electrons and holes. If you don't absorb, now for the first time, we have a very good reflector on the back. The reflector is outstanding. It reflects the heat back, and you get to use the heat again and again, and the light reflects back and forth many times, and eventually you get very, very high efficiency. And actually, the reflectivity is well above 92%. It's closer to 98%. This is very good, and this leads to something that could be called thermal photovoltaics. You have something very hot in the middle, and then you surround it with these photovoltaic films, They capture the high energy photons from the Planck distribution. They send the low energy photons back to the heat source. It gets reheated, rethermalized, back and forth. And the thermal radiation goes back and forth many times, back and forth. And eventually you get surprisingly high efficiency. But in this little chamber, there could be 280 suns bouncing around internally. But that's okay. You're stripping out 10% of that, making it into electricity. You end up with a very good efficiency and something that is reasonably small. But here is the efficiency projection. It depends upon how good the reflector is. Well, we needed a fantastic reflector to make this into a good LED because there's a photon gas inside and it bounces around, and so we need to have fantastic reflectivity. So I'm plotting the projected efficiency as a function of the reflectivity, and by the time you hit 95% reflectivity, you have 50% efficiency as a heat engine. So this is actually quite remarkable, and we're certainly going to go farther with that. And the goal is to beat the previous record. The previous record is 23% efficiency. So we think we can do that. But if you do this in a car, you end up with the car would need about a 50 kilowatt engine. And a 50 kilowatt engine, because you have so much intensity inside this little chamber, this can be done with a film that is about 70 centimeters by 70 centimeters. It would be very thin package, weigh almost nothing, and wouldn't have 23%. That's the current record. We believe this can go over 50% efficiency. There are other applications you can use this for, cogeneration. For example, unlike a power plant, there are power plants that are more than 50% efficient, but they're gigantic. We could achieve that kind of efficiency at a small scale. Let's say even in the home for cogeneration, you could produce 1,000 watts of electricity and 1,000 watts of hot water. That's one of the applications. Another application, since these are so lightweight, is for unmanned aerial vehicles. If you burn a liquid fuel, it has 50 times the energy density of a lithium battery. I understand there's a graduate of HKUST who's been very successful in this field with a lithium battery. But if we could use this thermal photovoltaics, it would allow the object to stay up for maybe 30, 40 hours. And also, there's even some interest in space use because they like to use radioactive pellets to make electricity. But it's very interesting. It sounds great, but there's a lot of competition. Where I live in Oakland, a block away from me is Broadway, and I get very depressed every time I go to Broadway. The city bus goes by, and it has fuel cells. So the fuel cells are also over 50% efficient. So this is very competitive, but it requires hydrogen. And there's great fertility, many new ideas coming out, and it looks like we will have new technology driving automobiles. So I'm not going to say anything more about the thermal photovoltaics because I'm more excited by something new. And because we're finally doing very well, we're approaching the theoretical limits, there's an old idea that becomes now very timely. And it's called electroluminescent refrigeration. And I'd like to use my remaining time. It's fun to do this, and I'm doing this with my student Patrick Brown. We're having a lot of fun with this because it's something very surprising. And the surprising thing is that an LED can be a refrigerator. Now I look up, I see we have some fluorescent lamps, but we're becoming more accustomed to LED lamps. And it can produce refrigeration. But before I tell you how the photons and LEDs produce refrigeration, I'd like to explain the traditional thermoelectric cooler. So these are used in technology wherever you need a cold temperature. They tend to use these, and the material is bismuth telluride. These materials have also become very interesting in solid-state physics recently because of the very strong spin-orbit coupling, and you have topological insulators. But they're really old materials. They've been used for thermoelectric coolers. Now let me explain how a thermoelectric cooler works. is very, actually quite simple. Let's say you have a current, but there's a barrier. Okay, and how are you going to get over the barrier? You need to get some heat from the lattice. You need some help from the Boltzmann factor. So you pick up some heat, you jump up, and then the current goes down. Okay. Now, to pick up the heat, it means that you've got the heat from somewhere. So this side becomes cold, and then when it comes back, it returns the extra energy back to the heat bath, and this side gets hot. So in this way, you have a thermoelectric refrigerator driven by a current. The electric current makes one side cold and the other side hot. Now, the way this is expressed is that the heat is often interpreted in terms of entropy. Now, I just realized that I'm not going to be able to explain entropy in this lecture. But think of entropy as just another way of describing the heat. And so the current is carrying the heat and carries it down and then returns the heat back on the other side. And it's dragging the entropy, it's dragging the heat from left to right. Now, interestingly, if you do it in reverse, if you make one side hot and one side cold, it'll actually drive a current. You can see this, the hot side will actually drive a greater current than the cold side will drive in the other way. So there's a net current. So you can use this, in addition to using it as a refrigerator, you can use this to generate electricity. So it is a known technology that is used a lot. This is a little bit of an idea how it works. You are dragging the heat. So this is representing the heat that you're dragging along. You're dragging the heat, but you're fighting losses. You're fighting resistive heating. Of course, that would defeat the refrigeration. You're also fighting the thermal conduction because you want one side cold, one side hot. You have to fight the thermal conduction. And what is helping you, though, is that you have a Fermi level that is a function of temperature. And so this is called the Peltier effect, that the Fermi level changes with temperature, which is for all materials true. And particularly true for semiconductors. And so they have figured out, and this by the way is a huge area of research, they have figured out that there's a figure of merit. So it has to do with this temperature differential of the Fermi energy, but it's penalized by electrical resistance and by thermal conductivity. So this is their figure of merit, and this is an old field, so they have achieved a certain figure of merit and they're sort of stuck with it. And it's called ZT. It's this figure of merit Z times temperature, or since I'm in a former British colony, I'll call it Z, temperature. And it's okay. It's roughly 1, but it doesn't work that well. It gives you only about 10% of the Carnot limit. It is, of course, very difficult to achieve the Carnot limit. So that's kind of interesting. You're dragging entropy from one side to the other. It's pretty good. Now, I want to switch to photovoltaic cell. Does entropy have any effect on a photovoltaic cell? So, in fact, yes. If we step outdoors, we would be in the sunlight, and the sunlight actually carries entropy. And the main source of entropy and disorder in the sunlight, it tends to come at you from all directions, particularly in the Hong Kong climate. Sometimes it's a bit hazy, and there's a tremendous resource of sunlight, but it is coming at you from all directions. This is true everywhere in the world, that it's not just a direct sun. There's a tremendous amount of sunlight coming from other angles. So the sunlight carries entropy, and most of the entropy is due to the angular uncertainty. And I can express it in the following way. If you go outdoors, you can see where the sun is if it's very clear, but you can't use that information. And so you have to be prepared no matter which direction the sun is coming from. So you're throwing away information. If you throw away information that is entropy, and that's the main source of the entropy, is the directional information. Now, of course, sunlight carries entropy. It's carrying entropy from the sun. The sun is a star. If you ask any astrophysicist, they will tell you for certain that the sunlight or starlight carries entropy. Why should our sun be any different? Our sun carries entropy. Now, here's the problem. It ends up inside the solar cell, and you have the photon energy, and then you're paying a price because it's not all the energy is available to you. You're paying a price because it's not pure energy, it's somewhat disordered. And so by the time you ask for the open circuit voltage, it is always less than the photon energy, is less than the band gap. No surprise. You're paying this price. It has to do with the entropy, mostly of directionality. And in the if you start, for example, with gallium arsenide, like these photovoltaic films, you're very lucky. The record, these are the record holders right here. The record is only 1.1, a little over 1.1 volts. So you're bringing in 1.4 volt photons, but they have entropy, so it's not pure energy. So you only get back 1.1 volts of pure electricity. So you can't complain, okay? And most of the entropy is due to directionality. You're uncertain of the directionality. Now I'm going to flip it around. I'm going to reverse everything. And I'll say, well, the solar cell is an LED, so now everything's in reverse, and I'm sending the sunlight back. And I say, well, everything's in reverse. Now I put in this voltage, 1.12 volts, and now I'm getting out the big photons. Okay, and this is really how it works. The LED and the photovoltaic cell are the reciprocal of one another. To produce 1.4 volt photons, you don't need 1.4 volts. Okay, and now this is the problem. Where's the extra 0.3 of a volt, almost 0.3 of a volt? Where's it coming from? Well, there's always thermal energy available. And indeed, the LED gets cold because you're taking out every photon, you're taking out 0.3 of a volt. And this is true for all the LEDs we have. In principle, the ones we have for lighting on the ceiling, and they could be little refrigerators. Unfortunately, if you go up and put your hand next to the lamp, it's hot. And the reason is that maybe the efficiency is not quite as high as it needs to be, because we're only getting 0.3 of a volt of cooling. So if we want to have net cooling, we better have an efficiency over 80%. And that's challenging. We're not quite there yet. So the LEDs are still warm, but if we can now make really efficient LEDs. And so it says every LED is a little refrigerator, in principle, if we can get the efficiency up. And I say, yes, we have fantastic efficiency now. This leads to this idea that we come in, we drive current, and according to the difference between the applied voltage and the LED and the larger photon energy, we have a certain entropy, and this is the entropy carried by photons. So this is very similar to the thermoelectric generator, where the entropy was carried by electrons. Now the entropy is carried by photons, and you should get cooling. Every LED should be a little refrigerator. Very surprising. And this is the amount of entropy it should be carrying. So that is rather amazing. And I should say there's an entire field for laser cooling, and you get such a tiny amount of cooling. They have conferences. Just running the LED efficiently is way more cooling power than the laser cooling. So it's just running a normal LED. So now I have to tell you a little story. So I hope you're maybe okay with the LED as a refrigerator, but I will tell you a little story that was told to me, rather remarkable story, by when I was young. I was maybe your age, but I was working at a place, and I met this old scientist from RCA Labs, and he was very distinguished, had many discoveries, but he told me what it was like in the early days. And he said in the early days, which is the 1950s, when the condensed matter physics, when they had a meeting, it's now called the March meeting, there are 10,000 physicists go to the March meeting. It's the biggest meeting of the American Physical Society. He says, well, in the 50s, there are only 25 of us. And I was there, and Shockley was there, and there were a few other people, and that was it. And he said that Shockley posed him the following riddle. Okay, and now I wish I could look it up. I think people have found some information about this. There was something published, apparently. But Shockley was teasing Al Rose. Shockley, of course, was a Nobel laureate. He was a very smart guy, theoretical physicist, and he teased Al Rose, and he said the following: look, suppose I have an LED, and it produces photons, and the photons then are captured by the photovoltaic cell, which produces electricity, and the electricity goes back and feeds the LED, and presto, I have a perpetual motion machine. And he teased him with this. What is wrong with this picture? And for certain, Shockley knew the answer, because he was like a good attorney. Never ask a question that you don't already know the answer to. I'm sure he knew the answer, but he teased Al Rose on this. But now we recognize that there's a germ of an idea here. This is not a perpetual motion machine, but this can be a heat engine. If, for example, the LED is hot and the photovoltaic cell is cold, you can generate electricity, and or if you drive a little extra voltage, you can actually use it as a refrigerator. It's kind of amazing. And I think the amazing thing is that I didn't know Shockley. I could have. I know people who knew him. But this is true throughout science, throughout physics. You go back and you speak to the older people, and they knew people that you can't believe they knew them, because these people are legends. And then they talk about the people they knew. And those are even legends further in the past and so forth. So we're all connected to the great scientists who lived in the past. And that's sort of the lesson of that. But here now, we've converted Shockley's riddle. We've converted this now to a heat engine. And in that we can get refrigeration from the LED, and then the photons go away, but we can recover most of the energy of the photons, send the energy back, and pay a very small energy price and get a surprising amount of cooling from that, refrigeration. Amazing. So part of it is so we recognize, like everything in thermodynamics, there's this symmetry. Everything's very symmetrical. The LED and the photovoltaic cell, they're really the same device. It's just one of them might be getting cold and the other one might be getting hot, and they are exchanging photons back and forth. And this is the sense in which I called the photons a working fluid. There's just these photons running back and forth and carrying entropy back and forth, and making a very efficient heat engine. So how good can it be? Well, we go back and we look at this concept. This was not just a photovoltaic concept, it was also an LED concept. It did rely upon having fantastic reflectivity on the rear surface, because you can see the photons are bouncing around many, many times. Now, why does this work? So I'm this is my prop here, and this is gallium arsenide. It's an actual living, breathing, it's a working model. I asked the people in the company to give me a dummy model, and they gave this to me, and I said, well, it was one of their films that didn't work, but I checked it with a voltmeter, it does work, and it gives it amazingly high voltage. And the reason why this works is this is a remarkable material. So usually the great things in science are not because we're so smart, it's because nature has been kind to us. And the way in which nature is kind, this is the most luminescent material that we know. Okay? We know many materials, they luminesce to some extent, but this is the most. It's been measured to be 99.7% luminescent. This is the highest. It's and what does it do? It enables the high performance solar cells, but also enables the high performance LEDs. So that's one requirement. The other requirement is we need a very good reflector, because we're going to have this photon gas. How do we get a good reflector? Well, if you woke up this morning, washed your face in the mirror, you were looking at a silver mirror. There was a glass, and behind the glass there's silver. That is an amazingly good mirror. And it can have a reflectivity over 99%, maybe not quite 99.5%, but we could raise it a little bit if we use, instead of glass, we use a lower index material like magnesium fluoride. But this gives you the reflectivity as a function of angle of the glass mirror. Not high technology. This is your bathroom mirror. There's a lot of tricks we can do to make that higher. So let me show you one of the tricks that we can do that's very easy. Is that, well, the photons, sometimes they can't get to the mirror. They suffer total internal reflection if you have a spacer that has a lower index. So if you have a lower index material, that's what I'm talking about with magnesium fluoride or silicon dioxide, the photons will actually reflect off the discontinuity between the high index and the low index and give you 100% reflection. And so it's only a small portion, the ones that are almost normal incidence, that are able to get to the low index mirror. And so the effective reflectivity gets much higher. Let me show you what happens. Is that all angles beyond a certain point, which is like maybe 20 degrees, all these other angles are 100% reflected. It's all total internal reflection. And if you're near normal incidence, it's still pretty good. It's around 99.5%. So if you take the average reflectivity is over 99.9%, which is amazingly low-tech way of getting a fantastic mirror. And so that's one of your requirements. Now, another requirement is you need to be a little bit clever about the texture. This is just a cartoon here, what the texture should be. There's a whole optimization needed, and this is actually supposed to be a video. Let's see if I can make this video work. I have to turn the arrow off for that. Let's see. There it is. Okay, with some kind of luck. So there's a very clever mathematical scheme for optimization that breaks the symmetry. If you have some kind of pattern, you actually want to have a broken symmetry pattern, and this is as it optimizes toward the highest performance trapping light, emitting light, and you need to produce a surface texture that is a little bit like this. This kind of a surface texture is needed. And it's actually a little bit more complicated, but we don't have quite enough time for that. So finally, what you end up with is a great LED, actually 97.5% external efficiency. And this is what's needed to get the refrigerator to work. And if you then plot this out as to what performance you can look forward to, here is the regular commercial thermoelectric, but you can see that you can do 3, 4, 5 times better with the, instead of an electron working fluid, a photon working fluid. And that's because we're finally controlling the photons efficiently. Now this plot, I need to explain the plot, it's a fraction of Carnot efficiency. So you can't really achieve Carnot efficiency, but it looks like we're getting to be about 0.4 of Carnot efficiency, so it's pretty good. And you could actually do even better if you could somehow make the mirror better than what I described. So this is roughly where we are. If we can improve the material or if we can improve the mirror, we can get into this regime where we're starting to really approach the Carnot efficiency. So there's a lot of work left to be done to get a phenomenal electroluminescent efficiency. Is just amazing. So let me arrive at some conclusions, and that is that we are, for the first time, making these really efficient photovoltaic cells and LEDs. They're the same device. But because of the worldwide situation, we need to think beyond solar. Oops, I see that my computer wants to shut down, so I'll just tell you what the conclusions are. And that is that we can go toward other non-solar applications. We can do the thermal photovoltaics for cars, and we can also do the electroluminescent refrigeration. So these are new opportunities that don't depend upon solar. Thank you very much for listening.
Thank you. That's a question that I always wonder, and that is how much energy is required to produce a photovoltaic cell compared with the energy that you get through its lifetime?
Yeah. The question that does come up from time to time. The reason is that the silicon solar panels, the kind that is being made in China and here in Hong Kong as well, the silicon actually takes a lot of energy to purify it. And so the question arose that in the old days, the bad old days, the solar panel would have to operate for 2 years before it recovered that energy. Nowadays, it's not quite so bad. So now it's maybe 6 months. After 6 months, it recovered the energy required to purify the silicon. However, this is why I keep pushing people toward these things. There's so little material here, and this stays at high temperatures for maybe 1 or 2 minutes, and then cools down. So people ask me, what is the payback time of these types of photovoltaic cells? And they're shy. Well, I think the payback time, I'm not sure is it 5 minutes or is it 10 minutes in the sun? So it can pay back. We need to get away from the old-fashioned silicon technology. That's been my editorial comment. But it's an uphill struggle. There are billions of watts of factories in China and elsewhere in the world. And now we're going to tell them, well, no, those are very inefficient. We need to go to something new and better. So it's very much an uphill struggle. And that's part of the reason why I'm looking for new applications. Because to go headlong and fight with a incumbent technology is difficult.
Okay, what if you turn the LED probably hard enough to turn it into a laser, and you don't have, there's no entropy?
That's right.
And then how do you balance the?
Okay, so that's a very good question, and it's a very instructive question. Thank you very much. So if I think the reason why my computer shut off is that here in the British system of electrical plugs, you actually have to press the button to get electricity, and I think we forgot to press the button. It gives you an idea. You get the electricity, and it's a sine wave at 50 hertz. You have a perfect sine wave, and it has no entropy. It's pure energy. Now, laser is very much like that, except instead of 50 hertz, it's 10 to the 15 hertz. You're getting a sine wave out of the laser. So one of the great laws of lasers is that in order to get lasing, you have to put in a voltage equal to the photon energy, because those photons are pure energy. There's no entropy associated with them. So in the laser, ideally in the laser, I would be putting in 1.4 volts DC, and I'd be getting out 1.4 volts AC at 10 to the 15 hertz at the optical frequency. And there's no entropy involved because it's pure energy going to pure energy. Okay? So that's the situation for lasers, but LEDs are very different. When you have an LED, it is not a beam of light. It has, it's sort of light all over the place. So I step into the elevator in this building, and I look up, and I say, oh, LEDs. And of course, the light's going everywhere. So there's a huge amount of entropy. And where do the photons get entropy? Well, in principle, they cooled. The LED is not as hot as we would otherwise expect because there's a little bit of cooling taking place every time the LED is emitting a photon. And so it's this interesting balance of entropies that gives us this new type of electroluminescent heat engine. Great question. Thank you very much.
Question about the luminescence efficiency in the first part. You talk about how do you measure it? You use a photoluminescence or electroluminescence?
Yes, that's a good question. So I'll tell you a little story about this company.
It also depends on the voltage, right?
Yeah, it's a very good question. So when the scientists and engineers, frankly, I hired the best I could get. Okay, the people and my co-founder, Harry Atwater, the best students who graduated from Caltech. In my case, I knew a lot of people at Bell Labs. The best people from Bell Labs, convinced them to join the company. So they were doing great stuff. But then it came time, they said, well, you need to break the world record. And the traditional way to break the world record is you make a photovoltaic cell, And you either get lucky or you don't get lucky. And it takes you several weeks to process. And after several weeks, you get to find out whether it was a record-breaking solar cell. I said, don't do it that way. There's a much better way to do it. Is take some light and just let it be like a solar simulator. Let it fall on the photovoltaic cell. And then monitor the luminescence coming back. And the luminescence coming back is like a voltmeter. So you haven't processed the material, you haven't done any work yet. And just by looking at the light coming back, you know ahead of time whether this is going to be a record-breaking solar cell. And so it was so easy for them to break the world record because they have, let's say they processed several of these films and one was a little bit better than the others. So they took the one that luminesced the best and they processed it, and they would know ahead of time what voltage, because the luminescence is like a voltmeter. They would know that ahead of time. So the reason why that idea worked is because it didn't matter whether it was electroluminescence or photoluminescence. Both of them were very good ways of pumping, and both of them would tell you whether it was likely to be record-breaking material quality. And so I would call them up from time to time, and I'd say, how are things going? And he says, well, we're just processing one. We already know ahead of time that it's going to break the world record. We know that ahead of time. And so you didn't have to try 100 samples. Okay? They've immediately focused in on a few samples, and then they would break the world record. Of course, then they had to send it to NREL. NREL had to validate the world record. But it made it very, very easy. And this is, I've recommended this to all the people at Berkeley who are working on photovoltaic cells, and they've all adopted this philosophy, is look at the photoluminescence. If you have good photoluminescence, it's going to be a good solar cell. And even if it's bad photoluminescence, it tells you exactly how bad it's going to be if you turn it into a solar cell. So it's a very, very useful diagnostic.
It's a photoluminescence you
Photoluminescence
mentioned.
or
Last time I heard somebody they say this should be electroluminescence. That's why I asked the question.
Well, I think the essence of what I'm telling you is that either one is good. They're both good, and they're both equivalent to one another. And
also, another question. Yeah, sorry. The concept of looking at the photon as a fluid looks like very nice. You can store the photons. That's very nice. The sun coming in, you store the fluid, and then you use it next time. But the material problem is huge, right? So that's really a material problem. You have something to store these kind of things for a long time.
Yeah, we have not solved the problem of storing light because it's moving at the speed of light. It's very difficult to store something moving that fast. And so the fluid, I didn't mean to imply that we could store the energy. What I meant to imply was that the photons would carry entropy and would act as a heat engine. I notice I'm getting a lot of questions from the professors in the front. Now at Berkeley,
one more.
The students get priority. Now are you sure you're a student? Because you might be a little older.
Yeah, I'm still. I would like to ask the question that I learned from you, that a good reflector is very important for the photovoltaic.
Yes.
And how about people to improve the efficiency of the photovoltaic by the light trapping? Is this contradictory to the concept, or we need to optimize for both and to achieve the highest record?
Yeah, it's very paradoxical. I didn't have time to cover that. So you're pointing out that at the same time that we're trying to get light out, we're also trapping light. And those two things seem like they're contradictory. And it's a little bit hard to explain. They're not contradictory. You have to do both. And let me take a shot at this. In equilibrium, because of the high refractive index of semiconductors, so this material, like most semiconductors, it has a very high refractive index, 3.5. Whereas you're accustomed to glass with only 1.5 refractive index. And when this is in equilibrium, exchanging energy with the vacuum, just that difference in refractive index implies that at equilibrium, you will have a tremendous amount of internal light. It's actually there's a formula for this that I introduced some time ago, 4n squared, where n is simply the refractive index, but it's a big number, it's 50. So if you have one sun coming in to be in equilibrium with such a high index material, it must have 50 suns trapped. Okay? And that's just a requirement for equilibrium. That equilibrium is always desirable if you want great efficiency. And so the flip side is yes, but if you have 50 suns trapped, that implies you must also be giving a certain amount back. And so you have this happy coexistence. At the same time you're trapping the light, you're also allowing exactly the right amount to escape. But it is a question that I often get, and now you make me wish that I had put that slide back in. But it's a very good question. Thank you.
You use the divergence angle as a measure of the entropy, right?
Yes.
In optics, we know there's a undo curve.
Yeah.
Which is the area times the divergence angle.
Yes.
So I can change the divergence angle by sacrificing area.
That's right.
Okay. So if I have a larger LED and a smaller solar cell, then I'm not transferring the entropy.
Yeah.
So area has to come in.
Well, the area does come in, but if you try to take advantage of the area, you find you have to focus. So for example, like the LEDs in the elevator, they're not actually going in all directions. They're actually more beamed. So if they're more beamed, you can actually focus down. But at the end of the day, it all balances out. And you build up with the focusing, you build up a higher intensity, and you have more free energy. And it's up to you, but you can't beat thermodynamics. You can sacrifice entropy, but then it forces you to work with only part of the emission from the LED. But it is a great lesson that some of the things in optics, which we think of as geometrical optics, they're rooted in thermodynamics. And we conserve, you called it H-undo, we conserve this it's on thermodynamic grounds. And if we somehow beat it by somehow getting a smaller angle, we would actually be violating the laws of thermodynamics. So there's a lesson in this, in that, and I guess this was not lost on Mr. Planck, is that you could learn a tremendous amount about physics and about thermodynamics by looking at light. So I've been fortunate, by some accident when I was a student, I became convinced the most important thing in light is thermodynamics. Here I am 40 years later, and it did work out that way.
The voltage loss, you see, looks like you said mostly is from the entropy of the light from the sun.
Yes.
But actually, when they also some from the electrons, the charge separation, they also
okay.
involve entropy loss, right?
That is a viewpoint that applies to not very good photovoltaic cells. And one of the things that I was taught by Dick Swanson. So Dick Swanson was a professor at Stanford, and he was a big solar cell expert. And he surprised me once. He said, you know, you don't need a p-n junction to make a solar cell work, and you don't even need a field to separate the electrons and holes. And what he told me was that you can separate the electrons and holes by diffusion. They just diffuse where they need to go. And in the course of diffusion, there's basically, it's something called the diffusion potential. And it's not a hard calculation. You can prove that it costs you, without an electric field, just by natural diffusion to the electrode, it costs you only a millivolt to separate the electron and hole. And so I think if you have, so this is, I get people mad at me because I tell them it should only cost a millivolt. And why are you working with a solar cell where you're wasting half a volt separating the electron and hole? It should not be necessary to use a lot of voltage to separate the electron and hole. And if it's a good material like gallium arsenide or silicon, you can get by with only a millivolt, and you don't even need a p-n junction. So there are silicon solar cells that have no p-n junction. They work perfectly well. So it has to do with if you have a solar cell where you have to give up voltage in order to separate the electron hole pair, you've done something wrong. Don't pursue that type of solar cell.
Thank you, Professor. I have a question. How to keep the LED in the low temperature and the solar cell in the higher temperature? And we know that for the solar cell, if we increase the temperature, the efficiency must decrease. So how can we solve this problem?
Well, I'm not sure I would regard that as a problem. That's really the mechanism we've been discussing. Let's say you believe in Shockley's, he had this trick question, Shockley's perpetual motion machine. It was very symmetrical. The solar cell and the LED were working together, and everything was in perfect balance. They exchanged photons. And then anything you do to upset the balance, it turns into a heat engine. So if you add a little voltage, it becomes a refrigerator. Or if you just make one hotter than the other, then it actually generates electricity. So I think that's the way to think about it. It's not a problem that one is hot and one is cold. You can use that. You can use it. Or if they're the same temperature, you can force in a little electricity and force one to become cold, the other one to become. So it's a little bit surprising and counterintuitive, but that was a reason for the title of.
Thanks, Professor. And compare with the laser and the LEDs, and in the process of the generating a laser light, and it should bring out less entropy from the material itself. So can we say that, and for the laser light, it contains less information than the LED light?
Well, yeah, it contains less disorder. The laser light is less disordered, but that came at a price. You need a higher voltage to operate a laser.
Means the input energy.
Well, you have to use the full band gap to get a laser, whereas in LED you can work with a smaller voltage. So yes, it's pure energy coming out of the laser, but it comes at a price.
And as for the laser, it brings out less entropy from the material itself.
In the case of the laser, you're not relying upon the material. You're putting in such a big voltage that it's already enough voltage to produce the photons. So you don't need to pull any energy out of the material. Whereas in an LED, you actually do have to pull the energy out of the material.
So there's no cooling effect for the laser,
Laser has no cooling effect. And if you work with anyone who works with lasers, they will tell you it gets very, very hot. Of course, and even when they're very efficient, they still get hot. Whereas with the LEDs, in principle, they could actually get cold as they work. It's very thought-provoking.
And so for the LEDs, if more entropy, if there is entropy bring out from the material, can we see that?
That's right. It pulls entropy out of the material.
If we regard the information as a kind of entropy, can we say that the LED?
What happens to that entropy is that in the LED, the light's going everywhere.
So more information.
That's so disordered. Where did that disorder come from? It came from the entropy in the lattice. And with a laser, that's not true. And in a laser, it's going in a very definite direction, so there's no disorder.
So the different direction of the light can be regarded as a kind of the information, right?
Well, I would call it the opposite of information, negative information, disorder.
Negative. Okay,
disorder, yeah.
Thank you.
Thank you very much, Professor. I just wonder whether we can pull entropy from the vacuum.
This is a good question for Professor Henry Tai. But I think in cosmology that happens all the time. Okay? So I urge you to be very successful in your classes and then go to graduate school, and then you take a graduate class from Professor Tai, and then you'll learn about how it is possible to pull entropy out of the vacuum and as part of cosmology, as part of the balance of the universe.
So which means a perpetual machine is theoretically possible.
Oh, no, unfortunately, that cannot happen. You cannot make a perpetual motion machine, but it's regarded as something that happened in the birth of the universe, there was a balance between the gravitational attraction of the universe, and it was balanced by other forms of energy. It's kind of interesting. So I think it gets us outside the topic, but it's a very fascinating question. Thank you.
Thank you.
Okay, let me thank the students. This has been a terrific set of questions. I don't always get this many questions, so I really appreciate it.
And let's thank Professor Yablonovitch also for an excellent talk. Very much.